Hello students, I am here for discussing on the topic of trench isolation and silicon on insulator techniques. Now, need of trench isolation. So the need of trench isolation generally depends on locus. Locus and its variation are not acceptable for IC with transistor density much greater than 10 raised to power 7 per centimeter square. This can be seen easily if we consider transistor size. Typical internal logic devices have a width to length ratio of about 4:1. For a 1 millimeter gate length, this corresponds to width of 4 micrometer. In this case, lateral encroachment of 0.3 micrometer per site might be desirable since it reduces the width of transistor by about 15%, but it is probably acceptable. On the other hand, if the gate length is 0.18 mm, this same enroachment is almost 85%, a clearly unacceptable amount. So in order to avoid this problem, we use trench isolation. Now, kinds of trench isolation. Simple shallow trench isolation process. This technique is similar to recessed locus, but a deposited rather than thermal oxide is used to fill the field region. After deposition, planarization must be done to remove the unwanted oxide from over the active regions. Now, after this, we are having deep trench or isolation process. Deep trench isolation process use trenches of fixed width. Now, this process is fabricated by starting from a standard locus structure. After nitride patterning, the trenches are etched. Now, the trench etch is done. It is typically done by simultaneously depositing SiO2 while etching silicon anisotropically. Next, a field implant is done. Preventing sidewall inversion become even more difficult as the aspect ratio of the structure increases. The implant is followed by thin local oxidation in application in which the trench fill is to be used as charge storage capacitors. Finally, a layer of polysilicon is deposited and etched back. If the polysilicon is thick enough, it will fill the groove. A second thermal oxidation can be used to complete the process by oxidizing the upper part of polysilicon in the groove. Often this is done as a part of locus process. Next is silicon on insulator techniques. The ideal method of device isolation is to encase each device in an insulating material. Several techniques exist for doping this in silicon. Generally, they are called silicon on insulator. Now, the technique is as follows. Uh, First, deep grooves are etched in the surface of the wafer. Now the wafer is oxidized and very thick layer of polysilicon is deposited. Now the wafer is turned over and mechanically ground until the groove penetrates through the wafer. Finally, the wafer is chemically polished and devices are fabricated in the isolation islands. Dielectric isolation has several drawbacks. The wafers are not as planar as normal starting material. This affects further process, that is lithography. Wafers made using DI process are expensive. Typical costs are over $100 per 100 mm wafer before any device fabrication. The isolation, if KOH potassium hydroxide is used to etch V grooves, the isolation density is not very large. So this is all about silicon on insulator technique and the dielectric isolation drawbacks. Thank you.